quantum numbers topic will be divided in two classes. Class number 1, we're going to study quantum numbers, what are they and where do they come from. This is today's class. Then, the following class, we are going to study quantum numbers, relation to orbitals and applications to electronic configuration. In today's class, we are going to study topics like Introduction to Quantum Numbers. With this topic, we're going to study things like definition of quantum numbers, importance of the quantum numbers. We'll see what they are important, what is important to differentiate the electrons present in the same atom by assigning them a unique set of 4 quantum numbers, and then the 4 types of quantum numbers. Second, we're going to study the relation between Niels-Bohr atomic model and quantum numbers. This will be very important to derive the principal quantum number. And third, we're going to study a little bit of Schrodinger Equation and quantum numbers. This will be very important to derive the 3 other quantum numbers and understand where they come from. From that, we're going to study things like Introduction to Schrodinger Equation, to know a little bit how it works, to learn a little bit of nomenclature related to the equation, and to have some idea how the equation is represented in Cartesian coordinates and then converted from Cartesian to spherical coordinates. And finally, use those ideas of the Schrodinger equation representing spherical coordinates to understand where the other quantum numbers they come from. Hey class, first of all, let's see what are quantum numbers. Quantum numbers are sets of 4 numbers. Each set of 4 numbers is used to uniquely identify an electron in a certain atom. If we could do some analogy between quantum numbers and something that you are already familiar, and a good example would be the Social Security number. For instance, in the United States, the government identifies the taxpayers by their Social Security number, which is a set of 9 digits. And why is that important to be identified by Social Security number? Because when the tax season comes, the government needs to track who is complying with filing taxes forms and who is not. Why is that important to label the electron in an atom? Because different electrons, even in the same atom, they have different energy values associated to them. One major consequence of each electron having different energy values associated to them can be reflected in the binding energy of a certain electron. Electron binding energy is also called ionization energy, and it can be defined as the energy necessary to remove a certain electron of its orbit in an atom of a certain element while that element is in the gas state. One good example about how the electron binding energy can be different between different electrons in the same atom is the lithium, which has the atomic number equal 3, so it has 3 electrons. The ionization energy to remove the electron located in the second electronic shell in lithium is around 5.39 electron volts, whereas the ionization energy to remove one of the electrons located in the first electronic shell of lithium is about 10 times higher. It's around 57.87 electron volts. This difference happens because it's harder to remove electrons from electronic shell close to the nucleus, because the nucleus has the positively charged protons, which attract more intensely the negatively charged electrons, which make them harder to be removed in comparison to electrons located in the electronic shells farther from the nucleus. At this point, it is important to point out that all these definitions about electron binding energy, they are all based in the Rutherford-Bohr atomic model. As it was told before, there are 4 types of quantum numbers, and each of these 4 quantum numbers has a name. Their names are: the first quantum number is abbreviated by the letter N, and it's called principal quantum number. The second quantum number is abbreviated by the letter L, and it's called orbital angular quantum number. The third quantum number is abbreviated by ML, and it's called magnetic quantum number. Finally, the fourth quantum number is abbreviated by the letter S, and it's called spin quantum number. The definition of principal quantum number is completely linked to the Bohr's atomic model. And on this point, it's necessary for us to define some postulates related to the Bohr's atomic model. For instance, the Bohr's atomic model has the following features. Electrons move around the nucleus in circular orbits, and each orbit has well-defined energy. Then, the energy of each orbit increases as the orbit becomes farther from the nucleus. The derivation of principal quantum number from Bohr's atomic model starts from the angular momentum of the electron. And the angular momentum of a certain electron is equal to m, which is electron mass, v, which is electron velocity, and r, which is the orbit radius where the electron is located. Then, that angular momentum, according to the Bohr's model, is equal to a multiple integer of 8 over 2 pi, which is also called 8 bar. And as shown in the equation 1, that angular momentum of the electron mvr is equal to a multiple integer with n of 8 bar. That multiple integer n, which can vary between 1 and infinity, it's equal to the principal quantum number. Just to remind, for those that are not familiar, 8 bar is equal to Planck constant 8 over 2 pi. The Planck constant 8, according to International System of Units, is equal to 6.63 times 10 to the minus 34 kilograms square meter per second. The principal quantum number n labels each orbit, or energetic level, where the electrons can turn around the nucleus. N can assume any integer values between 1 and infinity. As n increases, more energetic the electronic level is. Also, it's farther from the nucleus. We have seen that the principal quantum number n is related to energetic levels. Now we're going to see that each electronic or energetic level has a certain label according to the principal quantum number value. Okay, so based on the Bohr's atomic model, we have the nucleus here that's much smaller than the rest of the atom. Then we have the principal quantum number n. The principal quantum number n equal 1, that's the closest electronic shell to the nucleus. It can be labeled as key shell. Then for principal quantum number equal 2, the electronic shell can be labeled as L. For principal quantum number n equal 3, the electronic shell can be labeled as M. For the fourth electronic shell, the electronic shell having principal quantum number equal 4, it can be named as N. For principal quantum number equal 5, the electronic shell can be labeled as O. For the principal quantum number equal 6, the sixth electronic shell can be labeled as P. And finally, for the principal quantum number equals 7, the electronic shell can be labeled as Q. Now that you have already studied the principal quantum number n, we are going to need a little bit of quantum chemistry to keep going in our studying for the other three quantum numbers. And one of the principles of the quantum chemistry is that electrons can behave like a wave, okay? And this wave-like behavior can be described by a wave function, psi. That wave function psi can be evaluated by the Schrodinger equation. The Schrodinger equation in one of its simplest form is shown here. It's basically equal 8 hat times psi equals E times psi. Okay, let's see which of these terms they mean. Okay, so this capital H hat, it's what's called Hamiltonian operator. Okay, the psi, as we have seen, is the wave function that describes the behavior of a certain electron, and E is the energy of the system. Okay, so what Hamiltonian operator is? An operator is like a mathematical command or a mathematical order that is applied to a certain function. Okay, in this case, the function is the wave function psi. And the Hamiltonian operator, as you're going to see pretty soon, it gives some order to be applied over the function psi, and as we see in the right side of that equation, the result will be energy times psi. Okay, so the Hamiltonian operator is an operator associated with the total energy of the system. And in one-dimensional form, the Hamiltonian operator in Cartesian coordinates will be equal to minus 8 bar square over 2 times the mass times the second differential of that function over the second differentiation of the position, plus a function that describes the potential in function of the position. Okay, as we can see, so these are the operations that will be applied onto the wave function psi. Okay, as we can see, the Hamiltonian operation, it's a sum, so it's kind of like broken down in two parts. The first part, with the minus 8 bar square over 2m times the second differential over the second differential in relation to the position, is associated with the kinetic energy. And the second part, which gives a potential in function of the position, is associated with the potential energy. To be able to describe the wave-like behavior of the electron, the wave function psi needs to comply with some certain requirements, and one of that requirement is when the operator or the Hamiltonian operator is operating onto the wave function psi, the result of that mathematical operation needs to be the same wave function psi times a certain constant. The wave functions that have this property, that have this compliance to that requirement, they are called eigenfunction. In the same way, that constant on the right side of the Schrodinger equation that's multiplying the wave function psi, it's called eigenvalue. Okay, so in this case, the energy is the eigenvalue when the Hamiltonian operator is applied to the eigenfunction psi. Just to be familiar with the nomenclature, we just learned about the Schrodinger equation. So the capital H hat is what's called the operator. The wave function psi is what's called the eigenfunction. And the constant, the energy, that's the sought outcome on that equation, it's what's called eigenvalue. Just as a matter of curiosity, the word eigen comes from the German language and means self. So eigenfunction would be something like self-function, and eigenvalue something like self-value. In 3 dimensions, the Schrodinger equation looks like a little bit more complicated than we have seen before. So that's how it looks like in 3-dimensional. Basically, the kinetic energy part of the Hamiltonian operator needs to consider the second differential not just in 1 dimension, but also in y and z in 3 dimensions. The same happens with the potential energy part of the operator. The potential should be described in x, y, and z. And also the same happens for the eigenfunction, for the wave function psi. It needs to be represented in x, y, and z. And this version of the three-dimensional Schrodinger equation, it's what's called time-independent Schrodinger equation. There's another version, even more complicated than this, that considers the time on this equation. But this is the time-independent version, and it's enough for our study of the quantum numbers. Also, it's important to note that this version of Schrodinger equation is represented in Cartesian coordinates x, y, and z. And third, it's very important to understand that there is exact solution for the Schrodinger equation just for systems containing only one electron. For instance, a hydrogen atom or helium plus ion. The fact that Schrodinger equation is representing Cartesian coordinates x, y, z makes it harder to be solved. So to facilitate the things, the Schrodinger equation is converted from Cartesian to spherical coordinates r, theta, phi. Okay? You can find this conversion is like change of coordinates in any calculus book. Just here we have like an overview how it represents how they are related. So we have like a vector r coming from the origin, and this vector r, it makes a certain angle theta with the z-axis and a certain angle phi with the x-axis. So if you're interested to know how to make this conversion from Cartesian to spherical coordinates, feel free to consult any college calculus book. So this is how the Schrodinger equation in spherical coordinates look like. Take a time to take a look on this equation term by term very calmly and slowly, and you note that the Hamiltonian operator has changed a lot than it was before. Now it's represented completely in function of r, theta, and phi. Initially, when you first look to the Schrodinger equation in spherical coordinates, it may look like even more complicated than it was in Cartesian coordinates. However, it might be partially true. Being represented in spherical coordinates gives one certain advantage to Schrodinger equation, is that Schrodinger equation can be broken down or divided or separated in angular and radial parts when they are represented in the spherical coordinates. So this is a very important part that will be really important for us to understand when the quantum numbers they come from. Okay, so Schrodinger equation representing spherical coordinates, they give the chance to the variables being represented or broken down or separated, saying better, in radial and angular part. Okay, so that's it. The equation can be separated in radial part of the wave function and the angular part of the wave function. So as we have seen that the Schrodinger equation, when written in spherical coordinates, the wave function can be broken or separated in radial part and angular part. It would be really important for us to understand when the quantum numbers, the other three quantum numbers, they come from. Okay, so the radial part of the wave function depends only on the principal quantum number n that you have derived before from Bohr's atomic atom. We didn't need the Schrodinger equation for that. And also from the orbital angular quantum number L of the second quantum number. Okay, whereas the angular part of the wave function depends on the also in the orbital angular quantum number L, but the magnetic quantum number ML. Okay. And finally, the spin quantum number does not come from the solution from the Schrodinger equation. Okay, so this is all that we have for today. We finish our class by wrapping up the following concepts. First, The principal quantum number, it can be derived from the Bohr's atomic model by introducing the quantization condition to the angular momentum of the electron. Second, the orbital angular quantum number can be derived from the radial part of the wave function of the Schrodinger equation in combination with the angular part of that wave function of the Schrodinger when in the Schrodinger equation in spherical coordinates. And the magnetic quantum number can be derived from the angular part of the Schrodinger equation when represented in spherical coordinates. And the spin quantum number, it does not come from the Schrodinger equation solution. Next class, we are going to continue our study about the quantum numbers, and you're going to introduce the concept of orbital and see how the quantum number values are related to the orbitals, to which type of orbitals, how the orbitals are represented in relation to their respective quantum numbers, and define where the other quantum number, the spin quantum number, can be derived from, okay? And do other things like off-ball principle and how the quantum numbers are related with electronic configuration. Thank you so much. I hope you have enjoyed our class today. If your view, your time, your interest are really appreciated by us, and I really encourage you to like this video below and subscribe to our channel. I hope you have enjoyed this video. Thank you so much for watching. Bye.